Hello everybody and welcome to session number 23 of my lecture on statistical energy analysis and hybrid methods. So we are through most of the details of the theory and now it's time to start with the first examples of SEA models. And this is what this session will be about. We go to the details of some simple models. We stay still academic to present the idea and to present the methods that are used. There's no industrial example in this session, this will come later. However, it gives you a lot of hints and tricks and things and also limitations of SEA. So let's see what will happen in the next slides. Good. We start with a classic example. So what is so classic about it? It's so classic. It's a transmission loss test bench. So this means we have two cavities. They are connected by specimen with a specific surface area. And this is what we call the transmission loss test bench. So we have a source here in cavity 1, and we transmit into cavity 2 only via the specimen. And the idea is to understand the transmission loss of this installation in the middle. So as we have two cavities, we need the property of the cavity, and this is at first given by the modal density of the cavity with the formula derived in the sessions before, depending on the volume, the surface, and the perimeter. If it's an exact or good random cavity, as it has to be in the test bench, we could skip these parts here because they are not that relevant. We also need a relationship between the energy here in our cavity or system and the physical units. And that will be, in this case, as we're only talking about the pressure here, it will just be, oh, that's nice, some disturbance from the Windows system. So it will just be the relationship between the energy and the pressure in the room. So when we set up the SEA equations, that would be quite simple. It's a simple matrix. It's a 2x2 system. And we have this structure of the coupling loss factors. So we are not yet using the coupling loss factors because at the end of the day, what we are looking for is exactly, it is the transmission of this plate because that is what the test bench is about. And that means we just using the formulation to find a value for the coupling loss factor. Good. When we solve this and we consider the classical reciprocity relationship, we get this result. So we get the result for the two energies and with the given power here in the potential power sources here in our cavities. And with this given equations, which is a hell of combination of loss and anti-loss factors. Good. So in the next step, we know that we just have one source in one room. We are not using both cavities for power input. And this is just in sending room number 1. And using the formula, we would get this here as the energy result for a given power in cavity number 1. Okay, next step. We are considering that we have a very large room, so we just can consider only the first summand in the modal density. And again, now then we would also use the engineering unit relationship between pressure and energy as given before, and then we get this solution here for the pressure level in both rooms, depending on the input power. And we get rid of some of the modal density expressions here. Okay, so now if you know the test norm, the typical test bench result is the pressure level difference. So you measure the pressure level in room number 2 and you measure the pressure level in room number 1. And this is from the difference you would get finally the transmission coefficient and all the transmission loss. The difference of pressure level would be in the energy world, in the pressure scale and not in the logarithmic level scale. It would be the ratio of the squared pressures as given here. So when we use this pressure level, we get rid of all the power expression here. So the ratio of both pressures is no longer dependent on the power. So we don't care what power is introduced here. We just get an expression that's related to modal density in room number 1 and 2, and the coupling loss factor and the damping loss factor in the second room. Good. Okay. So next step then is, as we are interested in the transmission factor, we solve for the coupling loss factor from cavity 1 to 2. And this would give the following expression with many ratio of the different pressure expression here. In general, in the test bench configuration, the pressure in the second room is much smaller than the pressure in the first room. So that means we could neglect this part here and we would get this approximation. But please keep this in mind, because what is this expression? This expression comes from the back energy flow from the room number 2 back to room number 1. This is what we are neglecting here. So using this expression and assuming that it is a much lower level in the room number 2, we are ending up with this here. Okay, that's what I mentioned. There's a minimum isolation required so that this power backflow can really be neglected. Otherwise, both pressure level would be very similar. And now the question is, where do we get the damping from? We just assume only a surface absorption damping. And in this case, we would take the damping loss factor of the second cavity would be given by this surface absorption surface and the volume and the speed of sound at angular frequency. Good. So let's put all things together. And that means that we can calculate using this assumption, we can calculate the coupling loss factor. But as we are interested in the transmission coefficient, we take the relationship between the 3D coupling loss factor and the 3D transmission coefficient, and then using this, we get the following expression. So it's just simply the ratio of the squared mid-squared pressure multiplied by the absorption area in the second room divided by the surface area of our object under test. When we create the level version of this, so formulate the transmission loss of this from this transmission coefficient, we get this expression here. Pressure level in room number 1 minus pressure level in room number 2 plus the 10 times the 10th logarithm to the base of 10 for the ratio of the surface of the specimen and the room absorption area. This is exactly the expression of the test bench, which is described in the DIN ISO 10142. Perfect. So it must be true, because I mean our simulation SEA should give the same result than the classical test bench theory. And you see why many people say that room acoustics was somehow a foundation of SEA, because here we have really a random diffuse field in the room. This is where diffuse field ideas was coming from, and it was used here in this test bench. But what we're also learning is this formulation is only correct if we neglect the backflow of energy as it is given here. Okay, this was our first SEA example, and that's a trick. We only used, there was no coupling loss involved. The coupling loss was the thing that we were interested in. Now let's come to the basics of how do we calculate if we have an SEA model to solve. Just imagine that we have a typical symmetric SEA equation as given here. our state is given by energy divided by each modal density, and we have the power input on the right-hand side as excitation. In the first step, to set up our matrix, we have to identify the degrees of freedom. So what are the wave fields in our subsystems? Then we loop over all the single wave field or systems, and we determine the modal density and the damping loss factor, because that's what we need here in the diagonal. And by the way, in the state foundation. Then we loop over all possible junctions, and we add the coupling, we derive the coupling loss factors in these junctions. So for instance, if we have a junction that connect the wave field in system number 1, 2, and 4, we would get, let's say, a kind of junction matrix, which includes all the terms that are not the classical damping loss terms. And then we have to set up this junction matrix. So this is the part that let's say leaves each subsystem, and this is the power inflow from the neighboring and connected subsystems. And you see that this has a different sorting of degrees of freedom like our main matrix. So the idea is to distribute those coefficients at the right positions here in the matrix. This is quite similar to the typical procedure in setting up a finite element matrix, where we have to do the same sorting with the degrees of freedom of our mesh. So when we expand our junction matrix from the slide before, it would look like this, corresponding to system 1, 2, and 3. 4 and 3 is not used, and the others also not. Then the step number 4 is we add all of them to the main matrix, and then the last thing is to identify the load. So what power output do we have? Then we solve the equation, and we get the energies as a result. And from this energy, we have to do the post-processing. And that means at the first step to calculate the engineering units, so to say, pressure, velocity, or acceleration, or displacement out of the energy with the given relationships. But this is also very important. We can also, this is a very practical thing of SEA, we can calculate the power input into one specific subsystem. So it's the external power input, but these are the terms that define the power input from all the connected subsystems. So we can identify, so where is our noise coming from? Is it coming from this plate or from this connection or this hole? And this is very important if we do noise control. Good. So far for the procedure. Let's come to one very first example. I have to apologize. There's one drawback. I'm using a junction here that I'm explaining in this lecture. As I mentioned, because it's too complicated. However, you will find the details in my book, how this, or in the global literature, how the line junction could be calculated. We have a strange situation for plates. We have 4 subsystems, even though we have only 2 plates. The reason is that in SEA you usually separate between the bending wave field as one SEA subsystem and the in-plate wave field, a combination of longitudinal and shear wave. One further reason for this combination is that the line junction, when we use the diffuse field reciprocity theory, cannot be used for single longitudinal and shear waves. This is also explained in the book, and it comes with some, let's say, specific deficiencies, or let's say assumptions in the theory of using the diffuse field reciprocity. Good. So this is our state vector. And then I have to explain the nomenclature here a little bit. So EMV, that means that, and the first M is the index of the plate. And the second index is the index explaining the wave field. So bending, B for bending, and LS for end plate, longitudinal and shear, as explained here also. Good. As an example, so energy 2LS is the energy of the second in-plate plate, and it's the in-plane wave field. Load case, we have 2 load cases. We are exciting the plate number 1, putting energy to the bending wave field. And we're also using a force excitation of 1 Newton, also exciting the first plate. Good. So let's go to this. Just one final remark. This is the solution. All this what I'm showing here is simulated via the toolbox that comes with the book. It's called Piva. You will find it in the internet, and you will find also on the Python packages index that you can install it. But all the examples are given on the documentation page of Piva. Let's start with the modal density. Two very important things to note. There is a blue and green, that's the bending wave field of both plates. You see the modal density is quite high, much higher than the in-plane wave field because the wavelength is much smaller. And that's a very important thing to know and to keep in mind, it's constant. That's very strange. Yeah, the reason for that is the dispersion of bending waves. And that's also a reason why the statistics is not getting so much better for higher frequencies than for other wave fields because of this constant modal density. Okay, so then the modes in band, that's another option. Sometimes you write down the number of modes that you have in 1/3 of the band. That's also quite impressive to understand the statistics. You see that the bending wave, there are enough, around about 100 modes per productive band for both plates. So this is something that you could consider as a random subsystem. What is definitely not random is the in-plane wave field. Which you see that above 1 kilohertz, the first mode is occurring, and a reasonable number of modes for the in-plane is available at 2.5 kilohertz, which is quite high, or 5 kilohertz as said here in the text. Okay, coupling loss factors. We assume a damping loss of 1%. And when we calculate all the coupling loss factors, and there are a lot of them because we have 4 systems that could be combined, we get the most important one, which is the bending plate 1 to bending plate 2, or vice versa. Those are the baselines here. And we have a lot of other possible coupling loss factors that are combining the bending and the in-plane wave. But we also have a coupling between the wave fields in the plate itself, which is strange. So that means we have a coupling loss between the bending wave in the first plate with the inner let's say in-plane wave in the first plate also. But that's the reason, because we have two. It's one plate, but it's in SCA context 2 subsystems. The coupling loss factor are very strongly switching, but that's clear, and it becomes clear if we have a look at the reciprocity situation. I mean, this mode in band of the bending wave is many orders of magnitudes higher than this one, and using reciprocity is quite obvious why. If we change the direction of the coupling loss factor, there must be several orders of magnitude in between them. But what we also see is that if we change the presentation, I mean, the damping loss is around 1%, and our coupling, especially for the bending wave, is lower than the damping loss factor. So the weak coupling assumption that says that the coupling loss factors must be smaller than the damping loss factor, that's clearly fulfilled in our example here. Let's come to the first results. So when we solve the matrix, we get energy results. That's what we are doing. And again, we see that only the bending results got reasonable values. Well, okay, what does it mean in terms of an engineering unit? And this is what we do for the next step. When we use the relationship between energy and the velocity, we get this result as the engineering unit. So we can calculate an average root mean square velocity on our subsystems as given by the blue and green line. Good. When we now consider all these is for this classical power input of 1 watt into our bending wave field. When we use a power point force with 1 Newton, we use the infinite the power input into an infinite plate, which is given by this expression. And quite surprisingly, which is definitely not frequency dependent. So that means if we are calculating using this approximation, and you see the graph doesn't change. I hope to switch back and forth a little bit. You see the only thing that changes is the scaling. And that's clear because as this is not frequency dependent, we are just changing the scale of our energy results or velocity results in this case. Okay, so far for a simple structure-borne example. You must know that, I mean, if I talk about, let's say, a car, I mean, this is a very, very simplified version of a car. In a complex car body simulation, you must imagine that you have hundreds of plates that are connected. And this is the related SEA model for a full car body, for instance, of a car. It could be a fuselage, but it could also be several wards, which are a combination of several wards in a given situation. Good. Okay. Then we come to another example, and this is an important one because it directly reveals a weakness of SEA. If you do airborne solution, you always have this cavity-plate-cavity connection. And usually in SEA, only direct connection can exchange wave fields. Unfortunately, we also have to use an additional path that is bypassing the plate. And the best way to explain this is to have a look into our the transmission coefficient that we derived for plates when we discussed the junctions. So if you see here in our expression for the transmission coefficient, we have this blue area, that means this part is called the resonant path. So that is an excitation of waves in the plate that then radiate into the other cavity. This is why we call this resonant, because we excite a resonant wave behavior on the plate. We all know that the coupling loss factor from the plate to the cavity can best be calculated by using the radiation efficiency. So this is how this is usually done. And then we have the capability to calculate all the coupling loss factor between plate and cavity. The non-resonant part, so this is the upper part here, and the red curve, this represents the force motion of this plate, and this is the classical mass law. And we have derived the formula for the mass law before, and then also we have to use the 3D version of coupling between those fields, and then we get this relationship between the mass law transmission coefficient and our indirect non-resonant path coupling loss factors. And we have, again, then we have to do the angular averaging to get the right mass law for the diffuse wave field. Good. However, there's one important thing to note, and that's surprising to me that this is a mistake that is so often done. One consequence of the fact that the non-resonant path is somehow bypassed is that if you get the engineering results here on this plate, the forced motion is missing. It is not part of the SEA solution. And that's the reason why test results directly measuring the velocity here in this configuration cannot be compared to SEA results. Again, in this resonant path, the forced motion from the wave field is missing. However, this is very often done, but please keep this in mind. However, there is help available. One of my students created a formula that could overcome this, because if you just consider the forced motion of your plate due to the diffuse field in cavity 1 and or cavity 2, you just have to implement this correction. And if you add this velocity to the resonant velocity of our SEA solution, you will get a result that you can compare to tests. Later in the hybrid example case, you will also get a numerical expression for this specific correction formula. Good. So once we have understood our let's say plate cavity conjunction, it's time for a test case. And we come back to our transmission loss test bench, but now we really are calculating the coupling loss factor. We really calculating the property of this plate here in between. And we assume, let's say, 2 rooms with absorption areas 8 and 10 square meters. And you may note that this is exactly the area of this inner plate here. And you will later see why this is useful. We have a power input of 1 milliwatt, and we also consume that all damping comes just from the surface absorption, and then we will have this expression for the damping loss factor. However, also in the PIVA documentation, you will find this example, and it's called 2 rooms separated by a wall. When I calculate the results, and we just have a look first of all into the modes in band, you see these typical effects, and you also see why SCA was more or less invented in room acoustics. The modes in band of the cavities is very, very high compared to what you have on the concrete wall. And again, the bending wave is quite important, but you also see, due to the fact that the wall is very stiff, it is bending stiff because it is quite thick, the range between the in-plane wave and the bending wave for such a system, they are more or less in the same order of magnitude, and they change rules even in high frequencies. Good. As mentioned, the resonant coupling loss factor is calculated using the radiation efficiency. Maybe you have still in mind the Leppington approximation for the radiation efficiency that we are using, and but there's another option which is at least implemented in PIVA that's reformulated in an isonorm, which is also presented here. So Leppington is the blue curve with the radiation efficiency, and the orange curve is the Leppington is the isonorm. And you see they both agree quite well. You have this typical 1 area here in the high frequency field. You have this coincidence where the value is up to 3, and then you have this non-existent or very inefficient radiation in the low frequency area. Good. So with this coupling loss radiation efficiency assumptions comes the specific coupling loss factors. And you see that the coupling of factor of 1 to 3 and 3 to 1, so meaning, and this is the, let's say that's the mass law part, it's relatively low. And due to the very efficient radiation of the concrete plate, you see that the coupling loss factors of the wall connected to the cavities is quite high. And by the way, that is one reason why it is not the best way to live in a concrete building. Concrete is an excellent transmitter, an airborne and structure-borne noise transmitter. And I think some people that live in full concrete buildings are suffering from that. But keep in mind that just a 5 centimeter wall, the situation is slightly different if you have 10, 15 or 20 centimeter walls. Good. Now we come to the engineering results. You see that the pressure is constant in the first cavity. Why is that? Hooray, we just putting power into the cavity, and we have a frequency independent absorption or damping loss factor given by the absorption area. This is why this is a constant line. The situation is different for the second room, because this is the second room gets all the energy from the transmitted power through the concrete wall, and here you see this typical radiation efficiency shape with a dip in the coincident area. When we have a look at the velocity, we get this shape. Again, you can identify the coincidence here again, but keep in mind you could not compare that to test in this case. Good. So by proposing this example, you already have learned a very, very typical trick. So you might have seen that the absorption area in the second room and the surface area of our concrete wall is the same. What does that mean? That means this expression here is 1, and the logarithm of 1 is 0. So that simplifies the calculation of transmission loss in an SCA test case tremendously, because you just have to take You just have to take the difference between the pressure level in room number 1 and room number 2. And this is what we're doing here. And this is what we get is the blue curve. So quite low transmission loss for such a heavy concrete wall. And you see we are below the let's say the mass law. And the reason is quite clear. The reason is that the concrete wall is such a good radiator starting from this frequency. Another option to check for that is to use our power input formulation as presented before. So you see the blue line is what comes via the mass law from the first room, the power input in the second room, and the power input that comes from the wall, that's the orange line. This is this one. So it's in over a wide frequency range, it's higher than the mass law. The resonant transmission dominates here. Good. So far for the academic SEA examples. They are not very complicated, just cavity coupling, cavity plate, cavity coupling, and some examples, just the typical L-shaped structure monoid thing. But I hopefully have seen that you got the principal idea of how to set up an SEA model, how to identify the path, and how to interpret SEA results, especially regarding the velocity in airborne problems, which has to be corrected. Thanks for your attention. I hope you enjoyed this slightly shorter session. As you can see here above, next example will go through this very complete hybrid FEM and SEA example. I'm just presenting one example because we need a lot of tools to do so. However, in this example, I go through all the detailed steps of the hybrid solution, and I hope that the principal algorithm will become much clearer by showing this. I say goodbye and see you on the next lecture.